that you are trying to protect against errors, and you can add a little bit of redundancy to it in a particularly clever way, so as to allow the computer to also figure out exactly where the errors had occurred and not just if they had occurred in the first place. Ever since the times of Hamming, the applications of error correcting codes have gone way past the punch card computers. In general, you now talk about a more abstract setting where you have a sender and you have a receiver. In my slides here, I've chosen Hagrid, the character Hagrid from Harry Potter, and Harry Potter himself as the receiver. And the sender is trying to communicate to the receiver through a channel which is assumed to be noisy, meaning that some of the symbols that are sent through the channel can be replaced with other symbols. They can be random, or it can be an adversary noise. And so in this particular talk, I will not be focusing on particular applications like the channel can, for example, be a CD that can be scratched. It can be a faulty wire. It can be radio communication. It can be a letter sent by an owl through rain. So in our case, the topics that we consider are, in a sense, application agnostic, at least as far as the applications satisfy this template that I have provided on my slides. Hopefully that establishes a little bit what error correcting codes are used for. So now we will move to the more specific topic of algebraic geometry codes. And I will not introduce those in all detail. That would take me a whole talk to do. But what I will do is that I will introduce Reed-Solomon codes, which are the simplest possible case, the simplest possible example of algebraic geometry codes. And even those I will introduce using a concrete example. So here we would like to send the message wizard, the word wizard, over a noisy channel. And as you typically do with error correcting codes, you interpret the symbols that you want to send as elements of a finite field. In this particular case, I've chosen the finite field to be F29, which is just integers modulo 29. For those of you who don't know, you can think of them as numbers that start counting from 0 all the way up to 25, 26, 27, 28, and then loop back to 29. So now you can take these numbers, these finite field elements, and you can interpret them as coefficients in a univariate polynomial. This is where the Reed-Solomon case kicks in. And this polynomial that I have called f will be the message. This is the thing that stores the information that you would like to send over a noisy channel. And now, following the insights of Hamming, where we would like to add some redundancy to our message, the natural question is, well, how do we add this redundancy in a clever way? How can we utilize this polynomial structure in order to protect our information against noise? And in the case of Reed-Solomon case, the way you do this is to take your polynomial, which is a function, and you can evaluate it at many, many points. The more points you evaluate it at, the more redundancy you introduce, the more errors you can correct. So for the case of algebraic geometry codes, the intuition is very similar. So instead of, as is the case with Reed-Solomon codes, instead of considering a polynomial function, which you evaluate on a line, so to speak, you can think of algebraic geometry codes as taking more complicated functions, which can be thought of as fractions of multivariate polynomials, and you evaluate them on some algebraic curve. And yeah, that's what I was going to say here. The pictures that we see here might be a little bit misleading in the sense that everything is continuous. And of course, as I've explained with our example, we're working over finite fields. And so visualizing, for example, algebraic curves over finite fields isn't always as meaningful. I've tried to do so anyway, just for the sake of entertainment. So here I've found a curve over the finite field of 29 elements. I've called it the Christmas heart curve because, in my opinion, it looks like a Christmas heart. And this curve is defined as the set of zeros of the polynomial that you can see on the slides. And one thing to note here is that this curve has 41 points on it, which is considerably more than 29 points, which is what we had before. So if you remember, in the case of Reed-Solomon codes, since we are evaluating our polynomial in the elements of our finite field, we can never have more evaluation points than the size of the field in the first place. So in our example, we could never have more than 29 evaluation points. While here, while working over the same field, we can evaluate in more points, therefore thereby introducing more errors, thereby introducing more redundancy so that we can correct more errors. And the two main computational problems that are related to algebraic geometry codes are encoding and decoding. The problem of encoding we have discussed a little bit already. It consists of taking a function in whatever way it is represented and evaluating it at many points. And the problem of decoding is in a sense analogous or inverse, you could say, that if somebody has taken a message and encoded it using whatever code that is being used, and this code word, as it's called, is sent through a noisy channel so that some of the symbols have been replaced with something else. Our task is now to figure out what was the message that was used to generate the code word that was sent in the first place. And in the context of this talk, also in the context of this thesis, what we're trying to do is to find efficient algorithms for solving these problems. And there are many ways of measuring efficiency. You could measure time, you could measure the use of energy, which could be particularly useful for gadgets, for example. You wouldn't want your iPhone to go empty on battery every time you receive a WhatsApp message. But what we are doing in the context of this presentation is to measure the number of field operations that are used in the process. So that means we're counting the number of additions, subtractions, multiplications, and divisions. This concludes the first part of the talk, at least to some extent. I hope that the problem of correcting errors has been motivated, and also how algebraic geometry codes can be used for doing this has been outlined at least a little bit. So what I will do now is that I will mention two methods for encoding a certain kind of algebraic geometry codes. The first one comes from the paper that I wrote together with Peter Bellin and Johan Rosenkilde. And this paper considers encoding of algebraic geometry codes over a special kind of curve. This curve, or this special type of curves, is called CAB curves. I have a technical definition on my slides. I will not go through the actual technical details. What the important thing to understand here is that a CAB curve is defined by a bivariate polynomial, so a polynomial in two variables. And this polynomial has certain properties that it needs to satisfy. In particular, these properties have to do with the monomial support of the polynomial, saying which terms you're allowed to use. And secondly, the curve that this polynomial defines necessarily must be non-singular. I have found an example of a CAB curve just to show what they look like. So here I've found a polynomial over the finite field of 7 elements. So we're not over 29 elements anymore, but over 7, just to shake things up a little bit. And if you arrange the terms in this polynomial in a very specific way, so that the x degree increases as you go to the right, and the y degree increases as you go up, then you end up with this triangle shape that you can see of this polynomial. And this triangle shape is, in a sense, what characterizes CAB curves. The reason for considering these curves might not be straightforward at first, but it turns out that if you consider algebraic geometry codes defined over such curves, at least certain kind of codes, then the messages that you are considering, they are not complicated functions anymore. They are not complicated multivariate fractions, but they can be described using just bivariate polynomials. So polynomials in two variables, which makes them particularly well suited for computation. And the problem that we would like to do, I will demonstrate how to perform this encoding algorithm that we made up. And the way I will do this is to take this particular polynomial, and I will do it by example. So I will not present an algorithm listing, but we will just go through one example, hopefully conveying the intuition behind the method. Before I go there, though, it's important to mention that, of course, you can you can evaluate such a polynomial at many points just individually. That would be the simplest possible way of doing it. But this would be just expensive to do. In particular, if n is the number of points, which also bounds the number of monomials used in our polynomial, then evaluating such a polynomial at all of the points will cost roughly n squared operations. And this exponent 2 is what we're trying to compete with. So as long as we can do better, that is good. This is the same polynomial that we started with monomials arranged in the same way as I have described before, the x degree increasing to the right and the y degree increasing up. And what we can do now is that we can factor the powers of y out using distributivity, in a sense, which produces, in a sense, exactly the same polynomial, but now which can be thought about as a univariate polynomial in y, with coefficients being univariate polynomials in x. And the reason for doing this is that working with univariate polynomials generally is much easier, at least from a computational perspective. So there exist a lot of really efficient algorithms for working with those. And so at this point, when we have a bunch of these univariate polynomials in x, what we can do is we can take each one of them and we can evaluate them at all of the x coordinates present in our points. So you can think of our points, which you project on the x-axis, you get a bunch of values, and you can evaluate these univariate polynomials in x in those values. This gives you a bunch of tuples. So you have, in a sense, evaluated your polynomial halfway now. And by multiplying your powers of y back into these tuples, you get a bunch of univariate polynomials in y. And the only thing needed now to finish the encoding process is to take each one of these polynomials. For example, if you take the first polynomial, then your job is to evaluate this polynomial in all of the y coordinates that correspond to the first x coordinate appearing in our points. Similarly, we take the second polynomial and evaluate it at all of the y coordinates corresponding to the second x coordinate, and so on across our whole point set. So you end up with a bunch of values, and these values is what constitutes your code word. This is what you will send over your noisy channel in your attempt to protect your information against noise. So this method is fairly simple, which is one of the advantages of it. It would be easy to implement. And another advantage is that it is also efficient. How efficient it is depends a little bit on the context. So I've picked out two different contexts to explain efficiency here. The first one being that if we consider any reasonable curve, if we consider a curve which has sufficiently many points to be of practical interest, in particular that it has more points than the genus of the curve. The genus is just a number that you can associate to any algebraic curve. And also the number of points needs to be greater than the field size itself. If it's not, then why bother with algebraic geometry codes in the first place? You could have used Reed-Solomon codes. So in this case, the complexity exponent for the algorithm becomes 3/2, and this is to be compared to the exponent 2 that we had in the case of naive encoding. For those of you who are unfamiliar with this O tilde notation, I will briefly explain it now. The O tilde notation, also sometimes called soft O, is exactly the same as the big O notation, but it's more coarse in a certain sense that it doesn't see logarithmic factors. So you can just ignore logarithmic factors as long as you put this little tilde. Of course, logarithmic factors matter in practice, but exponents matter much more. And so this is what we focus on primarily. And secondly, if we now restrict the kinds of curves that we use, then we can get an even better complexity and even better speed, which is in a certain sense almost optimal. And this has to do with curves where the points form a structure that we call a semi-grid. And a semi-grid, I have an example of a semi-grid on my slides. A semi-grid is a point set where for each individual x coordinate, you have the same number of y coordinates appearing. So in the picture that you can see above, each single x coordinate has exactly 4 y coordinates associated with it. And that means that we can evaluate our polynomial efficiently at all of those points. You might then ask, well, are there any interesting curves that actually form a semigrid? And the answer to this is yes. Some of the most interesting curves for coding theory indeed are semigrids. That includes the famous example of a curve called the Hermitian curve, but it also includes curves like norm trace curves, which I don't know too much about, but I know people care about them. So this concludes the first method of encoding. It's a very simple algorithm, and it works for some of the most interesting curves, and it is efficient. What I will do now is that I will explain an alternative way of doing basically the same thing, but in a very different way. So we still are in a very similar setting. We have a bivariate polynomial, and we wish to evaluate this bivariate polynomial at many points on an algebraic curve. Now, though, we're going to throw a very strange assumption into the setting. We're going to require that all of the x-coordinates in our point set are distinct. That means that we never have 2 points which are right above one another. And your first reaction might be, well, that sounds absurd, because surely all of the interesting algebraic curves don't satisfy this property. And you would be absolutely right. But the interesting observation here is that by shifting your perspective a little bit, by doing a certain change of coordinates, you can actually ensure that it is the case that all of the x coordinates are distinct. So we can reduce the general case to this simplified case. And then you might ask, well, why do we want to do this assumption in the first place? And the reason is that we can utilize a very funny strategy where we take our input polynomial f, the polynomial that represents our message, and we try to reshape it into a univariate polynomial in x while preserving its evaluations at the points. And here is where it should be apparent that if the x coordinates of your points aren't distinct, then you cannot necessarily do this. This is where the assumption kicks in. So supposing that we are able to do this, supposing that we are able to find a univariate polynomial h, which evaluates to exactly the same things as our message polynomial f did, then the problem of encoding, the problem of efficient encoding becomes very easy, because we can just apply univariate algorithms. This is at least if the x degree of this univariate polynomial is sufficiently low, which is something that I will come back to later. But let's assume for now that that will always be the case. So also here, I will run through the whole algorithm using pictures. I will not present an algorithm listing. And what you see on the screen now is a box that represents the monomial support of our input polynomial. Just like we saw 2 slides ago, you can arrange the monomials of our polynomial in a box. Right? So now I'm just having a more low resolution picture of the same thing, where as you go to the right, you're considering monomials with higher x degree, and as you go up, you consider monomials with higher y degree. So suppose now that somebody comes to us and gives us a magical polynomial that we call reshaper. And this magical polynomial is magical for 2 reasons. It satisfies 2 properties. The first one being is that its monomials, its terms, are all bounded by this blue area that you can see on the screen. It's not very difficult to find a polynomial satisfying this first property, just pick any. But now comes the important part of having the second property satisfied, which is that this blue polynomial necessarily needs to vanish at all of the points that we are considering. So it needs to be in the vanishing ideal, or alternatively, it needs to evaluate to 0 for every single point that we are using in our code. Another property, which is like a half property, is that this little blue square that you see at the top, it's a little lonely monomial. This monomial necessarily is required to have a coefficient which is non-zero. That is very important. So assuming that somehow by magical reasons we're able to find such a blue reshaper polynomial, now we can do something funny. What we can do is that we can reduce our input polynomial, our message, with respect to this reshaper. So we can divide with the remainder, so to say, reducing the y degree of our input polynomial while increasing its x degree, producing a polynomial, which is the yellow one that you see. And I realized I can use this. I didn't need to go push the button all the time. This works. Nice. So back to the presentation. What has just happened? What just happened was that we started with a message polynomial with a high y degree. And then we reshaped it into a polynomial with a lower y degree and a higher x degree. In particular, you would like the ratios of these y degrees to be such that the y degree of the input polynomial shrinks by a factor of 2/3. So if you pick everything carefully, all of the ratios carefully, you can ensure that this is the case. And the price you pay for this is to increase the x degree. And the nice thing about this is that as long as you're able to find enough of these blue reshaping polynomials, then you can just keep doing this procedure over and over again, reshaping iteratively our input message polynomial into a univariate polynomial. And since in each iteration we are shrinking our y degree by a factor of 2/3, then it only takes logarithmically many steps to reach our desired final destination, which means that we're only adding a logarithmic factor to the complexity, and the big O notation pretends that this factor doesn't exist, so we're happy. So in conclusion, if everything works out nicely, if we have all of these blue polynomials somehow, then our algorithm is practically optimal. So the cost of it is soft O of n, where n is the number of points that we are using and also bounds the number of monomials that we're talking about. Still, this algorithm isn't ready to be used yet, because with this algorithm, there are certain caveats associated that require further research, you could say. And these caveats are, firstly, that it doesn't work for all points. Like as I said, suppose somebody gives us these reshaping polynomials, it might actually happen that these reshaping polynomials do not exist. What we have managed to show is that they exist for by far most point sets. So if you pick a random point set, then with overwhelming probability, you will be able to find these polynomials. So probably everything is fine, but algebraic curves, they are not random points. And so we don't really know how that interaction happens. So there are possibly tricks you can do by changing your perspective randomly somehow, but the details haven't been figured out yet. So this is very much work in progress, although this is a very interesting and powerful technique. And the second point to consider is that we actually need to compute these blue polynomials somehow, the reshaping polynomials. And the issue here is that we do not know how to compute them fast. We can compute them somewhat fast using linear algebra, for example, or slightly more sophisticated methods, but we are nowhere near being able to compute them in the target speed that we're aiming for, which is essentially optimal. For the purposes of error correcting codes, though, for the purposes of algebraic geometry codes, this is not an issue because we can always allow ourselves to spend some time pre-computing these reshaping polynomials. We can compute them before the communication protocol is deployed in practice. So that's perfectly fine. But for other applications that don't allow you to have access to the point set before a computation is to be performed, that is less desirable. That concludes the second third of the talk. So we're 2/3 there. Let me check the time. We're good on time. So, so far we have talked about error correcting codes. We have talked about algebraic geometry codes, why we care about them. And we have talked about how we can encode algebraic geometry codes, at least certain kinds of codes. What I will be talking about now is the second important problem associated with these codes, and this is the problem of decoding those. And what I will be talking about in particular are results from a paper that I wrote together with Peter Bellin and Johan Rosenkilde. And the kind of decoding problem that this paper considers is called list decoding. This word list decoding I haven't used before, so this is the time to introduce it. Indeed, there are many different ways you can consider the problem of decoding, and the most natural way maybe asks the problem of, or maybe asks you to, let me go into it from another perspective. Suppose that you have a message, And if we remember, the insight of Hamming was that you can add some redundancy to your message to protect it against errors. Now, another way of thinking about the same thing is that you can take your message, which is a vector, and you can embed it into a higher dimensional space. And you would like to do this embedding in a very particular way. You would like it to satisfy the property that all of the code words, like the places where the messages end up after this embedding, are far away from each other, so that if noise occurs, if a little bit of noise occurs, one of the messages will not end up close to another one. So to try to say this, to try to express this intuition more formally, we can take advantage of something called the Hamming distance, right? When I say, suppose you change your code word a little bit, I mean with respect to the Hamming distance, as it's called, which is a metric that you can impose on the space of all possible received words. And this metric is particularly suitable for the applications of errors. So the way the Hamming metric is defined is that if you have two vectors having the same number of entries, then the Hamming distance between these two vectors is defined as the number of entries in which these two vectors differ. And from this perspective, if you take a message, if you now embed it into your higher dimensional space, and if you send it through a noisy channel and one error occurs, that means that the channel, in a sense, pushes your code word one step in some random direction. If two errors occur, then you're pushing it two steps in some direction, and so on. At least that's one way of thinking about it visually. And so this is what I've tried to visualize on this picture on my slides. Here, this is supposed to represent this larger space of all possible received words. So the blue dots, they represent the code words. They're supposed to be where the messages land, and they are far away from each other with respect to the Hamming distance, which is symbolically represented using the Euclidean distance on the slides. And the orange dots represent the possible received words. And so if you, for example, look at, I can even point, I've been told, at this one, the right highlighted received word, what we can do is that ideally we would like to ask the question, can you find the closest code word to my received word? That's ultimately what we're seeking, right? If we get a received word and there is one code word which is close to it, it's probably that code word that was sent in the first place, at least if we make certain assumptions about our channel. But this problem turns out to be computationally intractable because it is NP hard, at least if phrased this way. So having a hope of solving it efficiently isn't all that reasonable. So another approach might be to rephrase the question. Instead of asking the question of how to find the closest code word to my received word, you can instead ask the question, given a received word and given a radius around it, like a bubble, so to say, a ball, can you find just any code words inside that ball? There might be one code word, there might be no code words, there might be multiple. In particular, if you look at the received word right here, I've drawn a circle of the same size as the one over to the right, but this received word has no code words close by, so we couldn't decode it using this perspective. Of course, you could then say, well, can't we just increase the size of these circles? And indeed you can, right? So if we increase them a little bit, then we can see suddenly this received word has exactly one code word nearby within this ball. And so it makes sense that we can decode this received word uniquely. But by increasing this radius, what has happened is that some other received words like this one now have multiple code words close by. And the consequence is that although in the drawing, one of them is closer than the other, that might not be the case in general. And in those cases, we might be forced to return a list of code words. At least that's the best that we can do. And hence the word list decoding. This is where the idea of list decoding comes from. So then a natural question to ask is, okay, we accept this setting that we get a received word we decide a certain radius around it, and we accept to find a list of code words within that ball. How can we do it efficiently? And this is what I will be talking about now. This is what the paper that I'm talking about is all about. And this paper, in its essence, it's grounded in a theorem by Guruswamy and Sudan. And this theorem, in a sense, decomposes the problem of decoding into problems that are computationally tractable. So what Guruswamy and Sudan say is that you will be able to find this list of messages that you are seeking as a list of roots of a certain polynomial, a complicated polynomial, but polynomial nonetheless. So I don't have the actual full technical formulation of the theorem, but I've tried to distill its essence on the slide. And the idea is that you're seeking a polynomial Q. This polynomial is quite complicated, although it is univariate in the variable z. Its coefficients are actually functions on our algebraic curve. So in the case of Reed-Solomon codes, those coefficients of the polynomial Q, they would be polynomials themselves. And these coefficients, they need to satisfy certain properties. In the case of Reed-Solomon codes, they need to have a bounded degree. In the case of more general functions on algebraic curves, there is a notion which is equivalent to degree that needs to be limited, needs to be bounded. So the idea of this theorem is that if we can find such a polynomial Q that satisfies certain size constraints, so to say, and if it also satisfies certain interpolation constraints, which I will not go into in detail, then it turns out that all of the messages that are inside of this ball around our received word will appear as roots of this polynomial, which suggests the following decoding strategy. The first step of the Guruswamy-Sudan decoder is to try to find such a polynomial Q. This is called the interpolation step, because Q, in a sense, interpolates a certain thing. Hence, by solving a certain interpolation problem, we can solve this part of the decoding problem. The second step of the Guruswamy-Sudan decoding algorithm consists of finding all of the roots of this polynomial Q, because this is where our messages are. And this is exactly what we do in our paper. It takes quite a lot of effort, so I cannot do it justice in this one slide, but I can talk a little bit around it just to leave a taste of what kind of strategies you would try to resort to when trying to do this efficiently. And considering the interpolation problem first, the interpolation step, the first thing that we do is to find a very special function that we call x that satisfies some properties that makes it very useful for representing other functions. Now, this function we can actually pre-compute, so to say, so we can spend a lot of time computing it. We haven't even considered the problem of computing it now that I'm thinking about it, but it's probably not all that difficult. So supposing that we have such a function x, I've said that x belongs to this letter f, the set f, which represents our function field. It's the set of all functions on our algebraic curves. Having found such a function x, then what we can do, it turns out that we can represent all of the objects that are required by the Guruswamy-Sudan theorem as f of x modules, which in practice means that everything can be represented as tuples or lists of univariate polynomials in x. And as we have learned before, working with univariate polynomials in general is much easier than working with multivariate things or even fractions of multivariate things. So having done so, representing everything as tuples of univariate polynomials, what we can do is that we can use a lot of sophisticated algorithms that already exist for working with structures that can be expressed using univariate polynomials. In particular, we use existing algorithms for efficient computation with matrices, computations with matrices where the entries are univariate polynomials computing certain normal forms of those matrices. And also we use techniques like simultaneous Hermite-Poirot approximation. That is a way of solving a bunch of congruence equations at the same time. So at this point, assuming that we have solved the interpolation step, we now have a complicated polynomial Q. And our task now is to find all of the roots of this polynomial, at least all roots that belong to our message space. And the way we do this is to take this polynomial where the coefficients are functions over our algebraic curve, and we can express them as power series in X. This is one of the nice properties that we imposed on X in the very beginning that allows us to do this. And so once we do this, now we are standing with a polynomial where the coefficients are power series in X. And then we can just use existing algorithms for finding power series roots of those polynomials. And once we have done that, now we have a list of power series. And doing a little bit of extra computation on top of these roots that are power series, we can convert them back into the setting where we came from. And ultimately, we find the list of the messages that we were trying to find. I will summarize now what the contributions of this paper are, or the highlights. What are the important things? Why it is a worthwhile result? The first point is that this technique is extremely general in the sense that it can decode absolutely any algebraic geometry code that you can imagine. So it's not limited to things like CAB curves like that I mentioned in the beginning of this talk. We can literally decode anything, and that's a lot. Secondly, our decoder is not the only one that can decode anything, but it is the fastest one. So anything else, any other decoder that can decode all the codes, all the algebraic geometry codes, we can decode it faster. And the third point is that there exist a lot of decoders that specialize in decoding specific families or even like specific algebraic geometry codes and utilize the structures in these codes. So, for example, there exist algorithms that specialize in decoding codes over CAB curves. There exist algorithms for decoding codes over the Hermitian curve. And what is nice about our decoder is that it is at least as fast, even compared to those specialized decoders. And that goes for absolutely all codes that we are aware of, except for the very simple example of Reed-Solomon codes, where we are just like half a millimeter away, so to say, for having the same speed. And I have one very busy slide, which I will not go into. I have mostly included this slide if it's going to be useful in the question round. But the takeaway here is that the speed of our decoder is, the complexity is linear in this factor n. Where n is the number of points on our algebraic curve used for decoding. And that brings me to the very last slide of my presentation. I am surprisingly on time, which I'm very happy about. So now I'll just briefly mention about what has happened, what are the main takeaways from this whole PhD project. And the first one is that we made a fast encoder for algebraic geometry codes over CAB curves. And remember that CAB curves include some of the most interesting curves when it comes to coding theory. The second takeaway is that we have a fast sort of encoding algorithm for CAB curves, you could say. We have a fast algorithm that can evaluate bivariate polynomials on random points. And this thing is probably usable. It's not unimaginable that you could use this for encoding CAB codes over CAB curves. But we don't know how to do it yet. And the third point was the one that I was just talking about, is that we can decode all algebraic geometry codes fast. This is a very powerful result. And lastly, this is the thing that I haven't mentioned at all so far. This is this paper that I haven't talked about. In this paper, which I wrote together with Johan Rosenkilde and Sven Puchinger, what we did was that we generalized another decoding method. So not a Guruswamy-Sudan decoder, but another method called power decoding. We generalized to basically all algebraic geometry codes. And this method has certain advantages, also some disadvantages, but I will not be talking about them during this presentation. And so at this point, I think I am ready to conclude my talk. And I would like to say thank you to everybody.
Thank you. I think you spent exactly 44 minutes.
Yeah.
So at least according to my watch.
Yeah, that's good.
Thank you very much for the nice, precise and clear presentation, even for someone coming from analysis. Okay, so we take a small break now. So how much time do you need? Is 8 minutes enough?
8.5.
We will reconvene at the 5 minutes to 3.
Okay.
For questions first from Arne Stoyan, and then from the from St. Markusen, and then from the supervisors.
Okay.
Okay. But we meet here again 5 minutes to 3. Thanks.
Thank you.
To state one rule, and that is that we should finish before 5 o'clock. So that is the last rule. And okay. Then I will give the word to you, Arne.
Okay, thanks.
Your questions.
So first, congratulations, Grigory. I think it's an outstanding thesis. And unfortunately, Daniel couldn't be here today, but he sent some comments. I think I'd like to read them. And I think the committee shares the feeling. The talk was also very clear. There's lots of examples. I like examples. That's very good. So the writing is excellent. The thesis is very clear with important results. It fills the gap between algebraic coding theory and computer algebra, aiming at efficient algorithms for algebraic geometry codes. Too long, these codes were not explicit enough. The thesis provides for decoding a setting which allows using modules over polynomial rings. This provides explicit forms of various spaces of function fields and gives fast algorithms. So these are both very good and promising contributions. It also paves the way for application of very long algebraic geometry codes in non-standard areas, other than correcting errors. So the rest of Daniel's comments and also questions, he also sent us some questions, or maybe I tried to divide them into kind of 3 parts. So let me start with the first part. So while too often neglected, the fast encoding of AG codes is very interesting, with a new application domain in verifiable computation. So a bit of context. Quite recently have appeared efficient cryptographic systems for proofs of correct computation, some of them from elliptic curves, some other derived from the decades-old PCP theorem. This theorem is now very practical, using some variant of it. The applied version, known as FRI or Starks, is getting quite popular and heavily funded in the blockchain space. These systems use very long Reed-Solomon codes, say 1 million, over a large alphabet, say Galois field with 256 elements. In these systems, only the encoding part is needed from the algorithmic point of view, and quasi-linear algorithms are necessary. Having quasi-linear time encoding for AG codes allows also using them in such systems. So now the questions, and these are from Daniel. Could Grigory say if the results could be extended to the M-variate setting, allowing a generalization of the contributions to non-plane curves?
Muted here. Hello. Now it works. Can you hear me?
Yep.
Yes, good. I'll repeat the question just to see if I've understood it correctly. If I've understood correctly, the question is, can we extend the results that we have for evaluating bivariate polynomials to a multivariate case? Is that true?
I think so, yeah.
Yes. I would say that you can approach this from multiple perspectives. So if you would like to approach this first from the perspective of the first paper I was talking about, encoding over CAB curves, then the algorithm that we are using is in a sense an extension of an algorithm by Victor Pan. And the algorithm by Pan works over point sets which are grids, multidimensional grids. And the reason for why it was interesting for our case is that we realized that it needs to be a grid in all of the dimensions except for the last one. And in the case of bivariate polynomials, this gives a semi-grid structure, which is very flexible. But as you increase the number of dimensions, you could say that the flexibility disappears a little bit. So whether this technique would be usable or not in higher dimensions depends very much on the point set that you are considering. You could ask, for example, if multidimensional. Can I maybe ask before whether the point sets that we would be considering in more dimensions have any particular structure? Are they also on an algebraic curve, or are they just some arbitrary points?
Yeah, I don't know.
Yeah.
Question for Daniel. Also.
Yeah.
Somebody else wants to make a comment about that.
From this perspective, I can only say that the technique from the CAB curve paper can be used for specific kinds, or is efficient for specific kinds of point sets, but is less efficient for others. And answering it in general, I am not capable of at the moment. But from the perspective of the second paper that I was talking about, where I was talking about reshaping, then it really seems that this is extendable to more dimensions. At least it should work in 3 dimensions. This has been sort of checked, and it seems that it is fairly straightforward to go to higher dimensions also. The only caveat there is still this notion of genericity or randomness, that so far we have no way of controlling for which point sets it works. We only know that it works for most point sets. And if the question is phrased in the sense of can we use this technique for general multivariate multi-point evaluation, the answer is not quite yet, if we want to be completely waterproof, but possibly we can, after all, if we inject some randomness into the system without breaking the complexity, but that remains an open problem.
Okay. So another question in this area, yet a natural question here is about the generality of the encoding. I find it strange that in this contribution, encoding a task apparently more simple than decoding is not quasi-linear for general AG codes, and that encoding here is fast for CAB curves only. What is going on here?
I'm not sure I quite understood the question you're asking. Could you repeat the question, please?
So it's Daniel's question. So a natural question here is about the generality of the encoding. I find it strange, or Daniel finds it strange, that in this contribution, encoding a task apparently more simple than decoding is not quasi-linear for general AG codes, and that encoding is here fast for CAB curves only. What is going on here?
Why is encoding fast for CAB curves only? That's a funny question to try to answer. Give me a second. So what makes CAB curves special? I don't know if this is, let me put it this way. There is one particular property of CAB curves that makes things simple, and the property is that one-point codes over these curves have a message space, which is a set of bivariate polynomials. And possibly other curves can be thought of in the same way. I don't know if they can. Probably some of them can. Probably many of them can't. But this is the property that we have been targeting in fast encoding, at least. That is half of the question. And then there was also half of the related to decoding. And I'm not sure I understood that completely.
Yeah, that's fine.
It's also not super easy to hear from me from here.
And Daniel had a technical question. Out of curiosity, you introduced CAB curves as being non-singular in the affine plane. This makes sense for defining the codes, but do you really need this assumption for fast evaluation?
For fast evaluation, I would say no, not at all.
Okay.
The only thing that we care about for efficiency is the semi-grid structure. As long as we're in a semi-grid, we're fast. And if it just so happens that some of these points are singular, from the point of encoding, I would say it doesn't matter at all.
Okay.
What I do not know, however, is if you have singularities, whether the message space consists of polynomials. This is not clear to me. But from the perspective of just evaluating bivariate polynomials on points on a curve, that should be fine.
Yeah, okay. Then we go on to the second part of what Daniel questioned. So if Grigory knows about towers of function fields, does he think he can get fast encoding, decoding for codes built on such function fields? The curves do not have to be smooth, plain model. I'm aware of an n-cubed complexity for building a code of length n on a Garcia-Stichtenach tower, and he gives a number of citations here, which is way too large for codes even of moderate length. However, for the tower considered in this paper, a lot of material is made explicit. Would it be possible to use techniques from the thesis for such families of explicit towers?
So decoding wise, I think the question is very nice. I think the question is very nice from the perspective of decoding, because the algorithm is completely general, the algorithm that we have. And so the way I would approach the problem personally is to say, well, give me an element in your tower, give me a curve in your tower, and just apply the decoding algorithm. And it should work, right? Because our decoding algorithm works for absolutely any curve. When it comes to encoding, we also have a general encoding algorithm as a part of the decoding paper. So we can still encode within the same speed, so to say. It is not quasi-linear. The speed is, as far as I remember, something like soft O of mu n, where mu is this smallest positive element in the y-stress semigroup of a special point that we pick, which I haven't really been talking about so far. But this would go for yeah, this is the answer that I can give now.
Okay, yeah, very good. Then going back to the 90s, one milestone at that time was to decode AG codes up to half of the GAPA design distance, but the complexity was n to the 2.5 for simple Hermitian curves. Reason algorithms such as yours clearly beat this, but in the context of list decoding algorithms, which somehow hide a genus penalty. In the context of unique decoding, can you use these fast algorithms for decoding up to half the GAPA design distance? It may be difficult since for unique decoding, there is this genus penalty, which may be hard to kill with fast methods.
So as far as I understand, and I have to make a disclaimer that I'm not too comfortable about this topic of how far we can decode, but I can say a little bit that we can mimic unique decoding by playing with the parameters S and L in the Guruswamy-Sudan decoding, where S is the multiplicity parameter and L is the list length. So by, as far as I understand, by increasing both parameters and setting them equal to each other, you can dramatically increase the decoding radius, and you can also somehow enforce unique decoding. But this will cost you a lot from the perspective of computational complexity.
Oh, okay. So I just had one final question. Then, so in your thesis, I'm looking at chapter 3. That's very interesting. So I just at the end of chapter 3, I don't know if you have it there, corollary 3.31.
Oh, sorry. In the end of chapter 3.
Oh, page 66. Yeah.
I think we were here. Okay. Page 66.
Yeah.
The next one. Okay.
Yeah, so you're using notions of like genericity of polynomials, and I understand that very well. And it means whatever it's supposed to mean in the current context. Also, like Schwartz-Zippel lemma is coming up. But then the statement of this corollary, I find it a bit, I don't quite understand, because you're saying, if this polynomial does not vanish, these points are good in a sense, or well chosen, then the following two problems can be solved with cost online soft O of n. But what happens if the points are not well chosen? So I'm used to more, anytime Schwartz-Zippel comes up, the language is usually it's a Monte Carlo algorithm or a Las Vegas algorithm. So Monte Carlo, it's always fast, but it might return the wrong answer. So Las Vegas, it's always returns the right answer, but it might take longer. So like what happens in this context here? Is it if the points are not well chosen, does the algorithm just take much longer to run? It's not linear time? Or does it report fail? Quickly reports fail, and then you can re-choose the points, or what's...
Yes, the short answer is yes, the algorithm will take longer to run, but for funny reasons.
66.
Yeah.
Yeah, I was gonna go a little bit up to a picture.
Oh.
This picture that we also have seen on the slides. Am I not screen sharing? Can you see my screen, Arne?
No.
No. Screen share. There we go.